Hi, in this video, we want to take a look at the geometric distribution. Okay, so here's the idea of what's going on. Let's say that we are going to inspect items coming off of a conveyor belt until we find a flawed one, a defective item coming off the conveyor belt. All right, so I mean, that's something we definitely want to know about, right? We want to have a probability, we want to have a mathematical model to understand like what is going on. Okay, so what we're going to do, we're going to say that defective or not defective is a Bernoulli random variable for each individual coming off the assembly line. And we're going to keep on doing this. And so what we're going to do, we're going to treat a malfunction as a success and a perfectly good device as a failure. Kind of a funny way that we do things, but that's how we do in statistics. We're going to go with our Bernoulli random variable over and over and over until we get a success. All right, so now this is important because we can use this distribution to understand, hey, I'm having too frequent of malfunctions going on, or okay, this is at a tolerable level. So remember, if I'm doing something like at a factory, a certain portion of the items coming off the assembly line will be defective. And we want to keep the defect rates below a certain threshold. And we can use statistics in the geometric distribution to kind of get an idea of what is the overall rate of defects that we're getting. All right, so some things we're going to make some assumptions. Our assumptions are, first and foremost, the Bernoulli trial for each individual is independent of all others. They're identically distributed. They all have the same probability of success. And that's really about it. We want them to be independent and identically distributed. And we're going to keep on doing this over and over and over and keep on drawing until we get success. Then we're going to count the number of times that either we drew, the number of trials, or we're going to count the number of times that we had failures. Both of these are equivalent of each other. They're shifts of each other. There's just one off as random variables. They slightly have different distributions, slightly different expected values. All right, so something to think about, if I'm looking at the binomial distribution, we know the total number of trials. We don't know how many are successes, how many are failures. With the geometric random variables, we don't know how many trials there are. We know how many successes there are. One, we don't know how many failures there are, and the number of failures really is the random variable. Okay, so let's do this. Let's manifest this first, and by going, I'm going to, each time I draw an item off that assembly line, that's going to be a number of one increase. And so we want to know how many trials is it going to take until we get success. So this includes the success observation. Okay, so here is our probability density function. So we're going to have 1 minus p to the power of x minus 1 times p. Okay, so what's going on here is that I have failure, 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 success. In this situation, the number will be a 6. Okay, if I drew again, I've got failure, 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 success. The number is going to be 5. And if the first one I grabbed is a success, then it's just going to be a 1. Now our cumulative distribution function, if we just do a little bit of calculus, is going to be 1 minus p to the power of x. Our expected value is 1 over p. Rather intuitive, if I have a 10% chance of failure, I'm expecting to see 10 come down the line before I get my first failure. And then our variance is 1 over p divided by p squared. All right, so now this is counting the number of trials until a success. The other way to do this is to count the number of failures. All right, so here, if I go failure, 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 success, in this situation, it's 3. Okay, and if I go failure, failure, success, the number is 2 in this version of it. And if I just, and the first one I grab is a success, the number is 0. Okay, so when if I'm counting trials, the numbers start at 1. 1 is the lowest number I can possibly get. If I'm counting the number of failures, then the numbers start at 0. 0 is the lowest number I can get. Now, you'll notice if I look at this, the variance for both versions are the same. The expected values have a difference of 1 because they're shifted over by 1. And if I look at the probability density function, you see I have x minus 1 up here, and I have just straight old x here. And that's because of the shift, just like in college algebra, horizontal shift. Okay, so now this is called the geometric distribution. Why do we call it the geometric distribution? Well, if you took Calc 2, you know something about geometric series, or possibly you looked at this in pre-calculus. If you took pre-calculus with me, you learned about it. All right, so let's consider the sequence of these numbers. I have a number to the power of 0, then a number to the power of 1, number to the power of 2, number to the power of 3, and so on. And this list is infinitely long. Okay, well, something I can do, I can represent the sequence with a formula where I can say that the nth term is b to the power of n. And in this notation, I'm saying that things start at 0, by the way. All right, so in this situation, b is a real number because we're keeping it real, yo. Hope that was fun. And then n is any number 0, 1, 2, 3, and so on. All right, so now let's consider the sum of the first n addends. All right, so this is not how I want to present. This should just be one sentence. I'll fix that in the documentation. All right, so now let's think about the situation where I want to add up the first n terms. So maybe I want to add up the first 10 terms, 20 terms, 30, 100, whatever. So here I'm going to say b to the 0 plus b to the 1 plus b to the 2 plus b to the 3 all the way up to b to the n. And I'm going to add them up. And I'm going to use sigma notation to make this a little bit more compact. Now, I'm going to do a trick. What is that trick? I'm going to go to the right-hand side. I'm going to multiply everything by 1. Right? Multiplying by 1 does nothing. Okay? Well, another way to represent the number 1 is 1 minus b over 1 minus b. Look at that. Is that the number 1? Yes, it is. It just looks a little bit different. Okay, so what I'm going to do, I'm going to take the right-hand side, all of this stuff, I'm going to multiply it by this fraction, and I'm going to do some simplification after that. Okay, so here, I have 1 minus b over 1 minus b, and I'm multiplying that summation that I've got. Okay, so let's go ahead and just, do a little bit of, middle school mathematics and put this into one fraction. So now I've got this into one fraction. Now, check out what I do next. I've got 1 minus b, and I'm multiplying by a parenthesis over here. Okay, so what I'm going to do, I'm going to distribute the 1. I'm going to distribute the negative b. So now I've got the parenthesis when it's multiplied by 1, and then I have b when it's multiplied by the parenthesis, and there's a subtraction in the middle. Okay. Now what I'm going to do, I'm going to distribute this b across the entire parenthesis. So you'll notice that down here, the exponents increase by 1 every single time. So here, this 1 became a b. This b to the 1 became a b to the 2. B to the 2 became b to the 3. B to the 3 became b to the 4, and so on. Okay, okay. Now check this out. I've got b to the 1, b to the 2, b to the 3, all the way down to b to the n, and I have exactly those terms over here. So if I look at this, I realize I have b through b to the power of n inside this parenthesis, which is getting hit by a negative sign. That means if I go through and I distribute this negative sign, I have a b to the 1, a b to the 1. B squared, it's hip to b squared. B cubed, b cubed. Next one would be b to the 4, b to the 4, and so on. So I see that a whole bunch of stuff will cancel out in the subtraction. Well, what's going to be left? Well, the 1 over here, it will be left over. And the b to the n plus 1 right here will be left over because they don't have anything to cancel out. Sorry, I'm having trouble getting it to highlight. But this 1 here doesn't have a 1 to cancel out with it. And this b to the n plus 1 has nothing to cancel out with it. Therefore, they're left over. Okay, so now I'm left with this formula. So if I take the summation of all of those terms of b to the power of some value, I'm going to get this like that. All right, so and now something about this. That b is called the base, and it's all about that base, Okay, so now what I want to do, I've got this formula. I have the summation is equal to this fraction. What I want to do is go, what would happen if I take the limit to infinity? Let's take it to the limit one more time. All right, so if I take the summation, I take the limit as n goes to infinity. We did note that with putting an infinite symbol on the top of the summation symbol. Now here, I'm just putting a limit out front of my fraction. Well, if you remember from Calc 1, this limit can kind of just come inside. And now I've got this fraction here is equal to the summation. All right, so now I need to think about what happens to this b to the n plus 1 as n goes to infinity. Well, there's 3 possibilities. If b is less than or equal to -1, then this limit doesn't exist. It doesn't make sense. What ends up happening is that b to the power of n plus 1, it bounces back and forth between positive and negative if I attempt to put in a negative value, and it gets bigger and bigger magnitude. The idea of a limit does not make sense. We don't have convergence. If b is greater than 1, well, and I just look at the formula, look at what we're doing, I realize I'm adding up infinitely many positive numbers that are greater than or equal to 1. The sum has to go to infinity as n goes to infinity. So therefore, it's just infinite. So that doesn't really help us. But now, here's the good stuff. Here's what we're really interested in. If b is between -1 and 1, then this limit goes to 0 as n goes to infinity. It follows that if I do the summation of infinitely many terms of b to the power of I, that ends up being this fraction of 1 over 1 minus b. Now, something that's important about this is that b must be between -1 and 1 for this formula to make sense. If I'm dealing with infinitely many terms, I have to have b between -1 and 1. Otherwise, this is stupid. Now, the formula up here, the formula that we derived with this summation equaling this fraction, that works for any base at all. It doesn't matter how many terms we have as long as it's a finite number. All right, so the next thing to think about, well, let's start working with this with a probability. Okay, so now what I'm going to do, I'm going to take the formula that I showed you a moment ago for the probability distribution function, where I have the probability of failure to the power of x times the probability of success, like this. Now, I'm going to choose where we're counting the number of failures because this is a little bit easier to work with the summations. Okay, so here I'm going to add up all the probabilities together. Remember, if I'm dealing with a probability, if I add up all the probabilities over the entire sample space, it's going to add up to 1. If it doesn't add up to 1, then I know there's a problem. Now, also, probabilities are always greater than or equal to 0. This follows from the fact that all the terms of 1 minus p and p are positive. Therefore, this isn't an issue. Okay, so when I get to here, I see that I have a summation, and there's a constant value here. So I'm taking the sum as x goes from 0 to infinity of 1 minus p to the x and then I multiply by p. Well, you know what? I'll go ahead and just factor out that p, pull this out front. Now, I have the summation as x goes from 0 to infinity of the probability of failure to the power of x. Now, 1 minus p is between 0 and 1. Therefore, I may automatically apply that geometric series formula that we just worked out a moment ago. Okay, so here, remember it's 1 over 1 minus b. So here is that fraction for us. Like that. Okay, so now I'll look at this and I realize I have 1 minus p. Well, that's 1 over p. And so that just ends up being 1. Okay, so this actually defines a probability. Good. Now, what about the expected value? All right, so for the expected value of the geometric distribution, what I'm going to do to make this a little bit easier on the computations, I'm going to say that Q is the probability of failure. All right, so then my formula for the expected value is that I'm going to take the sum x times probability of failure to the power of x times p. Okay, so now I look at this and I can see that I can factor out p. Okay. When I look at this part, this x times p to the x, that looks a lot like a derivative, but not quite. It's almost a derivative. What's wrong is I need a -1 in the exponents. So what I'm going to do, I'm going to factor out 1q, and so now I have this formula. So I have that. Okay, so now when I look at this, that's a derivative, right? So I'll go ahead and rewrite this part as the derivative of q to the power of x. I'm taking the derivative with respect to q. This is very important. I know that when you took calculus, it was always take the derivative with respect to x. Well, because of what's presented to me, I'm not doing that. I'm using the formula and I'm paying very close attention to it, that this is the derivative with respect to q. The x is treated as a constant for this situation. Okay, so now I have a summation. I have a derivative, and then I have q to the x. All right, so a big result from calculus, this is important, is that when I'm doing calculus, if I have a limit and another limit inside of that, I cannot switch the order of limits. I can't do that in general. But there are times that I can, and this is one of those times. I chose to do this because this is one of those times. All right, so something I want you to pay close attention to is that this summation is a limit as we go to infinity. Now here, this is a derivative, and all right, so derivatives are also limits. Hopefully you remember taking the limit as, h goes to 0 or the delta goes to 0, something like that. Okay, so calculus is the study of limits. That is the true, correct way to think about calculus. If you try to look it up, there'll be a long definition about it. Calculus is the study of limits. Any other approach, you're going to screw something up. Okay, I have a limit with a summation and a limit involving a derivative on the inside. In general, we cannot switch the order of limits. Here I can, because of material beyond the scope of the course. So here I can take, because of material outside the scope of the course, I can switch the order so that the derivative is on the outside of the summation. We cannot do this in general. So here, when I do that, I see that I just switch the order. All right, so now, once I have a summation of q to the x, I go, hey, that is a geometric series. I have a formula for that we just worked out. All right, so look, I'm going to replace this summation with the appropriate fraction. Boom, we got this. All right, so now, once I've got this, I'm going to take a derivative because it's easy peasy lemon squeezy. And I can see I get 1 over 1 minus q squared, like that. And I realize that 1 minus q is the same as p. So I get 1 over p squared. And now I just simplify it using basic fractions. Boom, we've got our expected value. So it's going to be our expected value is going to be the probability of failure divided by the probability of success. Now, to compute the variance of the geometric distribution, I'm going to modify a formula. So remember that the variance of a random variable is equal to the expected value of x squared minus the expected value of x squared on the outside. Okay, I'm going to modify this slightly. Okay, what I'm going to do, you see how I have expected value of x squared inside here? What is negative x plus x? That's 0, right? Okay, so here inside the parenthesis, I've added 0. So I have not changed anything in my formula, but it's a different presentation. Now, I'm going to use the fact that expected values are integration, and with integration, we can break things up. Okay, so when I do that, I'm going to see that I'm going to have an expected value, and I'm going to have the expected value of x times x minus 1. Now, why do I want to do this? What I'm going to end up doing is I'm going to do something very similar to expected value, but I'm going to do a second derivative. I'm going to have a first and a second derivative going on. This is a very common trick with discrete random variables, by the way. So now, this I know, because we just computed it, this is the same as that, but squared. All right, so I know what that is. This part, I still need to work this out. So let's go ahead and work this out. I'm going to find the expected value of x times x minus 1. All right, well, by the definition of expected value, I just take x times x minus 1. I multiply by q to the x because that is from the distribution function. And then I multiply by p. I need to get this infinite summation to find out what the expected value is. All right, now I look at this. I realize I can factor out that p. And I also realize that this is almost a second derivative. Whoops, that's not what I want. This part here. This is almost a second derivative. The only thing that's off is I need a -2 in the exponents. So what I'm going to do, I'm going to factor out 2 of my q's out front. So boom, you'll notice I factor these out like that. All right, so now I notice that this is actually the second derivative of q to the x with respect to q. So I'm going to replace all this stuff with the corresponding second derivative right here. Okay, so now I have a constant times a summation time with a second derivative and then the actual items on the inside. Okay, so remember, this is an infinite limit. I'm adding infinitely many terms up. Here, this is a derivative, therefore it's also a limit. In general, I cannot switch the order of limits, but I can on power series interval of convergence, which we're on. Therefore, I can switch the order of the summation and the derivative so that here I have the derivative outside of the summation. So now I look at this and I go, hey, this is a sum of geometric terms. It's a sum of geometric terms. I have a formula for that. Since I have a formula for that, I'm going to use it. I know that this is going to be 1 over 1 minus q. All right, well, I'll go ahead and take the second derivative on that. Boom, I'll get this. Now I'll go through and I'll just do a little bit of simplification. And I can see that the expected value of x times x minus 1 is 2 times the probability of failure squared divided by the probability of success squared. Okay, so now what I'm going to do I know that this, my variance, is equal to all this stuff. I'm going to go through and I'm going to plug in 3 items to replace these terms. All right, so here are the 3 terms. I replace the expected value of x times x minus 1 with what we just found. I slap in the expected value of x for the expected value of x, and then I square the expected value of x to replace the squaring term. Now I just do a little bit of college algebra. Wham, bam, we get our variance. The variance is going to be the probability of failure divided by the probability of success squared. All right, so now that establishes the distribution. The distribution is a probability. It also gives us we've got the expected value and we have the variance. Now let's talk about using this in R. All right, for the geometric distribution, it's going to be geom, G-E-O-M for it. So once again, things are very similar to the other 4 functions for distributions in R. We have D genome, we have for the density, we have P genome for the cumulative distribution function, we have Q geom for quantiles, and we have R geom for random number generation. So X and Q are going to be quantiles. And in R uses the failures representation, not the trials representation for implementation. Remember that our probability needs to be strictly greater than 1, but it can actually be equal to 1. That is allowable. But in that case, we, on our first grab, we end up getting a success. So it's not very interesting. All right, so for the density of the geometric random variables, I plug in the values I want the probability for, and then I give the parameter, which is just P, and we can see it gives us the values. You'll notice that there are 11 terms because this is 0 to 10, including 0. So this is the probability of seeing 0 failures. So it's 50-50 to have 0 failures. And then it decreases geometrically all the way down. Now for the cumulative distribution function, once again, I give it the numbers I want, and this gives me the probability of being less than or equal to the particular value. So we can see that, at 0, 1, 2, 3, 4, 5, 6, 7, that we are virtually guaranteed to have 7 or fewer failures. We can get our quantiles once again, and we can do a random number generation. Now you'll notice about half of these are 0, and that comes from the fact that 0, when I set the probability equal to a half, then I'm going to have about half of them are going to have 0 right off the bat. That makes sense, though. Okay, so now let's go ahead and do an assignment. All right, so select a Bernoulli random variable that you can implement, you can observe very easily and do repeatedly. You need to decide which aspect is a success, which aspect is a failure. Now, you're going to do this either it's like flipping a coin or waiting till something breaks or something happens, something that you can model randomly. Run your event until your first success. Record the number of trials or failures. Repeat this until you have 30 observations. Make a table of your counts. Plot a bar plot of your data. Now, on this next one, take your sample mean, set it equal to the population mean for the distribution, and try to estimate what P is. Then use your estimated value of P to create bar plots showing the density of geometric random variables. How well does your data match the bar plots that you made from the data. So how well does data and theoretical distribution match up? And then go ahead and run the example code of the 4 functions, and just to see how things go using your probability instead of the 0.5. Well, that's all I've got for you. Take care and goodbye.